Do you guys remember the definition of what makes something polynomial? That makes it a function, but that doesn't necessarily make it polynomial though. Sometimes we write polynomials like this: a certain number of x4s plus some x cubes plus some x squareds plus some x's plus a constant term. Does that make sense? That's like a polynomial. Hey, Fonda. What's up?
They know the answer.
Sure.
The argument with, one being a prime or a composite, the argument with triangular numbers, is one a triangular number or not?
So yeah, define triangular number.
Okay, a triangular number is the number that can, how a square number you can make it into a perfect square. A triangle you can make it into a perfect triangle. So 3 is a triangular number. The next triangular number would be 6, because you would add 3, almost like building a
Like
pyramid.
2 plus 2 plus 2, you're saying?
No. So
Okay, nope.
3 makes a triangle.
Okay.
So this is 3. So the next triangular number is actually 6. So the next one
it's 10. Okay, we did this in our sequence,
So
last year.
would 1 be a triangular number? Because I always thought it wasn't, but then when the kids went and got a list, it says it was.
Well, it doesn't make a triangle unless the number
Circular number. Okay, let's take a vote here. Triangular number.
No.
Okay.
Okay,
These guys say no.
we're going to say no.
Say
Okay,
no.
next.
It's decided.
That's
Give me a dot.
like I can see, unless you drew your dot like a triangle. I can see where it
Triangle
come
like
from,
dot.
but no, it wouldn't be a triangle.
Fair enough.
It's a happy triangle.
Alright.
She's like, oh, you can't have a triangle. Anyways.
Okay. Back to polynomials. Does it make sense that a polynomial is like a certain number of x5s, then some x4s, then some x3s? The common mistake that some people sometimes make is they forget, like, let's say I write x to the 4 plus 7x squared plus 3x plus 2. How many x thirds are sitting there? And you have to account for those. Because there was one test question on your last test where if you missed that, you probably got the wrong answer. Everybody's looking at me like, yep, did that. Okay. The next unit we're going to focus on are graphs that are not polynomial functions. There's going to be a lot of similarities. There's going to be a lot of differences. We've actually covered some non-polynomial functions last year. I kind of went a little further last year on certain things, knowing we were going to cover them again this year. So you guys actually have, believe it or not, a lot of experience working with some of these functions. Okay. Let me give you some examples of non-polynomial functions. So these guys up here would be polynomials. Absolute value functions. Not a polynomial function. Fair enough. Square root is what we're going to talk about today. And reciprocal are also ones that we've kind of talked a little bit about last year. So today's goal, I want to focus on what are called radicals. So let me start with some review from last year first. Okay. Do you guys remember all these terms like index, radical, radicand?
Yeah.
Okay. If we don't write a number right here, it means it's a square root. Okay. Typically, just so you know, we're going to work with square roots a lot. We could, in theory, work with cubed roots and fourth roots and fifth roots, but we probably won't. Other skills that we worked with was being able to combine radicals of certain types. 5 root 7 and minus 1 root 7, can they go together?
No. Yes.
Yes, they can, because they both have root 7s. So if I asked you to add these guys, then you have 4 root 7s. Can you add these guys, though?
No.
Okay.
Wait, what?
Because the root is not the same. Or the
You can
radical is not the same.
No, there's a 5 and a 3. Okay. Same thing here. If you have a cubed root of 5x squared, cubed root of 5x squared, these guys can go together, but these guys can't because this one's got a 4th root and a 5th root. That makes sense. Okay. Another term that you might know is the term mixed radical and entire radical. Okay. The difference between these two is that this one, you have the number pulled out front, and this one, the leading coefficient is been put inside. Do you guys remember doing something like this where you'd say 18 is really 9 times 2? And then 9 actually square roots to the number 3, so that's where this 3 came from? Okay. Let's just practice a few of these then. You guys think you could convert from one form to the other without me showing you? No, give it a try. Or should I do one or two?
Like a couple.
Alright, what do you guys try then?
16 times like 7. That's a big number.
Oh.
212?
I'll just throw the answers up here one at a time as I get them.
5 versus 2. Yeah, I'm getting good at this. Stop thinking out loud!
Sorry, Kayla.
Close. No, no. No. Yeah. Oh, that makes sense.
Wait.
Oh, I'm 10.
Yeah, if you have a number sitting out front, like this 4 or this 11, you square it to put it under the inside, and then you times it by any number that's currently there. So like for this one here, I did 11 times 11 times 8 to get the 968.
How would you put the n back on the inside? Would you just put it?
You'd have to put it in as a squared
Oh,
now.
this one's where?
You'd have n squared inside.
Charles,
Yep.
there's like a negative under. Oh, never mind.
It's a cube root. You can do a negative cube root.
How do you do this? How do you do it?
Do it.
Is that a 10 or a 6?
Would we do that one that your cursor was just over because that's
This one right here? Okay, for anyone who's looking at this guy right here, this is a cubed root, which means that you're not looking for numbers like 4 and 9 and 16. You're actually looking for like triplets. So 1, 8, because that's 2 times 2 times 2. 3 times 3 times 3 would be 27. Does that make sense? So this one's a bit different. Because of the fact that you have negative numbers, you can actually reduce a little differently. Okay, well what if I did factor trees? What if I said this was equal to 27 times 16? So this guy is equal to 3 times 3 times 3. So what you could do is you could take out a negative 3 and then leave it at the root of 16.
You can't leave negative 16 in there.
You could have actually done that. You could have also done 3 third root of negative 16. You can do the third root of a negative number though. Because you can do negative times negative times negative. 3 negatives then stays negative. Does that make sense? We just got to put the 1 over 2a inside the brackets 3 times.
Times 7. Is that a nice number? Oh, you just, fraction. Okay. Yeah.
I might do this next one like this. So you've got to take this 1 over, I think that's 2a. You got to take the 1 over 2a and times 2a by itself 3 times. So 2 times 2 times 2 will give you 8. A times a times a will give you a cubed. And I'm just going to put it underneath the 7a. It would also be valid to write it like this. 7 over 8 a to the negative 2.
1 minus 2.
Do you guys remember like exponents? If you have an a on the top and 3 on the bottom, they kind of like they cancel. Yeah, and then negative 2 just means that it's like there were 2 on the bottom. That'd be a valid way of writing it.
go 8.
Reciprocal.
I got 7a over 8.
Okay, so I left the 7 and the a there.
Okay.
The 2a on the outside, I have to put it on the inside like 3 times. So 2 times 2 times 2 is 8.
So I have to worry about the 1 because
I skipped the 1. The 1's kind of pointless.
it's okay.
Because I guess I could have done like
The 1 versus triangle.
1 times 1 times 1, but that's kind of silly to put all that there.
Yeah. Okay.
And would you, if it was a big, say like 2 over 3, how would you do that?
2 over 3 on the outside.
Yeah.
Then you'd have to do 8 on the top on the inside and 27 on the bottom. Does that make sense? Because 2 over 3 times 2 over 3 times 2 over 3 would be 8 over 27. That makes sense?
Like 2x.
How would you do
Well, what
this?
about like if there's a 7a
Or you
and
go
there's
2x
also
cubed.
2x cubed.
No, because you. Once you take
I
out
think it's 2
the,
over 3.
like
So.
if you had 2x.
Okay, what does 128 divide by? Does it divide by 27? No. Does it divide by 8? Oh, it does.
2x cubed on the outside, then you get a cube it again.
8, 16. Then you have x cubed and x. So it's 2x root 16x. Like that. That's what this is.
4x cubed or cube root 2x.
This one right here? Because you took out an 8.
Well,
I split it up into 8 and 16.
I just did 4, 4, 4.
Oh, because I forgot that 16 can keep going, didn't I?
That's all I meant.
Never mind. 16 can break up into 2, 2, 2, and 2. Right? So I should be able to take out another set here. And you're right, Nicole. My bad. 4x cubed root of 2x is even better. Thank you. 16 also has 8 inside of it, so you can do it again. Do you guys recall these skills? Like they're not the point of what we're doing here, but like they will come up occasionally. So we can work on these if we need to, but please don't feel like, oh my goodness, I don't remember how to do all of this. I can't do this next unit. It's just this may come up once in a while. Okay. Okay, here's where I want to start. If you have a graphing calculator, I want you to graph for me 2 different graphs. One of the graphs is going to be the square root of x, and the other one is going to be the cube root of x. Do you guys know where to find cube root on your calculator still?
No.
Okay, good. Math.
Oh, you did 4. That's weird.
I'm just going to do them one at a time if it's okay here. So I'm just going to do square root of x to start with. Do you guys get this?
Yes.
Okay.
Yeah, why it does.
Okay, I'd like to. That's what I want to do. I want to talk about why it does this. Okay. Let's look at a table of values. I'm just going to go to the table here. As I go to the table and I kind of go around the middle here, hopefully you notice something about all of your negative numbers. Okay, here's the first point I want to make. This has not come up very often so far, but the domain of the square root vending machine as a function, there are certain numbers that you cannot plug into this particular machine. Negative numbers cannot go into square root graphs. Does that make sense? Because you cannot square root -1 or 2 or 3 or 4. So the first number that you can actually start square rooting is 0 actually. Because you can square root 0. What would the domain of this graph then be? X is greater than or equal to 0. Does that make sense? That's the domain of this graph. So for the first time, we have some major restrictions on our graph. We can't do any single number we want. Okay. Another thing that happens with this graph is that it starts to take a bit of a weird looking shape like this. It starts just heading slightly upwards. Here's maybe what helps describe that. It goes through the point 0, 0. It also goes through the point 1, 1. The reason why is if you square root 1, you get 1. But then check out what happens when I start doing 2 and 3. I don't really get nice even numbers. When's the next nice even number I get? 4, because 4 actually does square root to become 2. So this point here should be at 4, 2. When's the next point that's actually going to be like even? 9, right? Over here, 9 will be at 3. Is this graph going to keep going up, but slowly? Does that make sense? Like, when will the graph have a height of 5? Yeah. When will the graph have a height of 10? Yeah, so if I even wanted to change my graph, if I want this thing to actually get to an actual height of 10, I'm going to need to make my x 100, and hopefully you can see that it will eventually get to that height, but it's going to take a while. Does that make sense? Okay. Can we also do the cube root graph then? So then, if you haven't done this already, where is it? Math, cube root x.
This one can be.
This one can be negative, yes.
It's times by negative.
So what ends up happening on this graph is it has a very similar shape in this quadrant over here, but you actually are allowed to have negative numbers. Okay. Like for example, the cubed root of -1 is -1. Does that make sense? The reason being is that -1 times another -1 times another -1 would equal -1. So you can actually do cube roots with negatives. So when you look at your table of values, 0 gives 0, 1 gives 1, -1 gives -1. When's the next time we get like a nice even number though?
Probably 8.
It's at 8, yeah. Because 8 is 2 times 2 times 2.
Yay!
Ta-da!
We did it.
Does that make sense? Okay. I'm just going to fast forward in my notes to another picture somewhere. Where is it? Can you guys find this slide? I'm sorry it's way out of order here. I think now's the time to talk about this slide. Let's do it here. This is basically what we just did. Okay. I need you now to know these next two non-polynomial graphs. One is the square root function. The next one is the cubed root function. And I need you to know the properties of these graphs. Okay. So back to the square root graph. X has to be greater than or equal to 0. But I never talked about range. Does it make sense that the range has to be greater than or equal to 0 as well? You can't really get a negative number out when you're done. That being said, on the cubed root graph, you're actually allowed to have anything you want. Okay. Fourth root, if we were to go that far, is kind of like a square root again. You can't have negative fourth root numbers, but you can have negative fifth root numbers.
Isn't it just that like if the index is positive, it can't be a negative number?
Even is the word you're looking for. If the index is even, you can't have negatives. Does that concept make sense? Okay, so I just need you to know those properties. From now on, then, when I ask you domain and range questions, the domain, I don't need you to write me the domain as an element of the real numbers on something like this. Okay, tell me what x can be, basically. Does that make sense? Like, sometimes maybe teachers may have asked you to do x as an element of the reals and x is greater than 0. I don't actually need this part, if that's okay. On this guy right here, though, when you can have any number you want, then you still should write it down. And same with range, yeah. Okay, let me hop back here. Last week we talked about something called an inverse. There was a question on your test where I asked you to figure out the inverse. And I think a lot of you were like maybe a little stumped at first, but then when you had to solve it, it isn't that hard. An inverse, if I were to give you like say y equals x squared, inverse means to flip x and y around. So if I were to flip x and y around, you would have x equals y squared. Then how do you get y back by itself? You square root it. Well, these guys are actually inverses of each other. If you were to take a good old parabola and take a square root graph, they're inverses, with one exception though. This graph right here doesn't go below the axis. Do you see how it's like a sideways parabola? You can see that? So like, here's an original parabola. Here's a square root graph. If we were to include the bottom half of it, it would basically be a sideways parabola. Why don't we include the bottom half of it? Sometimes we've learned though that like the square root of 3 is equal to, I heard it there. It won't be a function. That was actually another question on your quiz that I think a couple of you guys got tripped up on. If we were to actually try and draw the second path down here, it wouldn't actually be considered a function anymore because it doesn't pass the vertical line test. Remember that phrase from previous years maybe?
Oh yeah, you can't have like them lining up.
Yeah. So like if you were to have a graph like this graph is perfectly fine. But if you were to have a graph like this is not a function because like right here it doesn't pass the vertical line test. Because here you have an x value, an x value, and an x value that gives 3 different y values.
Can you do that?
Well, you can't do that and call it a function still.
Oh, okay.
Like you could make that graph, but we wouldn't call it a function anymore.
Possible.
Because the definition of a function is that one x value gives back one y value. And here, one x value is actually giving back three y values. If you like the vending machine analogy, it would be like I put in $1 and the vending machine is broken and it gives me back 3 bags of chips. Awesome function. But technically it's not a function anymore. Like it's supposed to be a loony gives back a bag of chips, not a loony gives back a bag of chips and a chocolate bar and a bottle of pop. Good vending machine.
That's good. We should do object lessons.
Yeah, let's try that out.
Well, let's go find a vending machine.
Make it force the thing for a while.
Okay. So does anyone get this concept then that these things are actually inverses? A parabola we can actually have both halves to. The square root function, we'd like to have the second half of it, but we can't because now it's not a function. So that's why we only get the top half of it.
That's the only reason we can't have
That's the only reason we can't. It won't be a function anymore.
Okay.
Now, let's say you want to actually make the sideways parabola show up. There is a way of doing this. Okay. If you go in your calculator, just go back here, and you go y equals the square root of x, that would give you the top half of the function. Well, if you want the bottom half of the function, just go negative square root of x. Because all that's going to do is flip the graph over, and now it should hopefully look like a sideways parabola. You see how that works? Well, we don't actually want this bottom half, though, because now it's not a function. Does that make sense? And our unit is on functions, so that's why we only get to keep the top half of it.
So then why would you necessarily like want to have
I mean, if you wanted to prove that you could make this look like a parabola, then maybe I could throw an x squared here, and you might say, hey, look, it looks like this guy right here is just turned sideways over the line y equals x. So like I could even do this maybe and say, do you see how there's like a mirror there and how they're flipped over? Does that make sense? Okay. Okay, moving on then. You can even do this with graphs that are translated. What would the equation of this parabola be? I know it's kind of cut off on this picture, but could you guys figure out the equation of this parabola? Yeah, I'd say x squared plus 4, because it's been moved up 4. Well, how would that affect this graph here? If this was y equals x squared plus 4, okay, well, the inverse would be, let me just like put a little note here. Let's flip x with y. You'd now have x equals y squared plus 4. How do you get y back by itself then?
x squared square root.
Square root.
Subtract
So x
4.
minus 4 equals square root.
Would you subtract 4 first then square root? Or
We did this exact question on your test, yeah. That's why I wanted everyone done first before we talked about this. Okay. Now this may seem weird, but it may help explain why the negative goes this way. What do negative signs inside the function do to graphs? Move them
Right.
that way. Do you see how that fits? There was a plus sign right here that caused this graph to move up. But when I rearranged it algebraically, it got turned into a negative sign, which makes sense because negatives make the graph go that way.
Wait, what's the point of like flipping and then flipping it back?
We can.
I'm not sure what your question is. We only flipped it one time. Like this was the original guy right here, and I'm just taking this guy and flipping it to become the square root graph.
See how we did y equals x squared?
Oh, okay.
Then we do it.
And then to get y back by itself? Because the way your graphing calculator works is it always says y1 equals, y2 equals. So like if you have this equation here, this is a valid equation. But we don't normally type in x equals stuff. We type in y equals stuff. That's why we have to rearrange it.
Why didn't we use the first one?
Because the first one is this graph right here,
It's changing.
and I'm hoping to get this guy down here.
Why, for, like, don't you have to square root the other side too for the bottom there?
To get the bottom side right here,
Yeah.
like what I'm kind of starting to draw down here.
Yeah, because you wrote
Just be a negative square
x equals y squared plus 4, and then you square rooted.
Okay, so you're suggesting like the positive negativeness here? Like how you can do plus or minus square root? Is that what you're getting at?
No, I'm talking about the y. Y is square rooted also.
Because when I square root y squared, it becomes regular y.
Oh.
Because that was the point. In order to get y by itself, I had to subtract 4 and then square root y.
Okay.
That's why y is now by itself. That makes sense. Pretty.
Do we have to do a flipping, or can we just look at it and say square root?
Often you can just look and, yeah. I mean, I'm hoping you get to understand the reason why it's doing this, but if you can just look at it and say, hey, this is a square root graph been moved over 4, you're good to go. That actually kind of leads next into my next slide here. I want us to sketch these two graphs. These two equations look the same though.
Yeah.
So I need to be more specific here. I did this on purpose. On one of the equation, I want it to be the square root of x plus 2 with the x plus 2 over the square root sign. And then the other one, I want it to be square root of x and then add 2. You guys see the difference there?
Yeah.
So that's why I left it on this way on purpose, because this one right here, this x plus 2, is inside the function. What would that do to the graph then? Okay, so it should hopefully be over here. Whereas the other one would take the graph and move it up 2, so it would be like up here. You guys see the difference there? One of them moves it backwards 2, and one of them moves it up 2. So now,
Same to me though.
Okay. Oh, yes.
How do you get that?
Yeah, I was.
that doesn't make sense.
Both square root of x.
Okay, so remember how a square root of x graph normally looks like this? So the purple one, I've just taken where it normally would have been right here, and I've just pulled it back 2 and made it go roughly like this. Whereas the one where it's square root of x plus 2, I just moved the graph up and then had it start.
And the tests are different.
Oh,
Like
okay,
brackets
I
around
see what
what's
you mean.
being
No,
square
he tried to make me so. Oh,
Should I, like, let's graph them in your calculator just to make sure we're in agreement here. Do the square root of x plus 2. So see how, like, with the brackets here, the plus 2 is clearly inside the brackets? Whereas here, it's the square root of x, close the brackets, then add 2. So hopefully you see the difference. Here, this one starts over here, and then this one here starts up at 2.
When you write them in the tests or the stuff, or you put them.
I will make sure I'm clear, yes. I did this on purpose. No, I did this on purpose to make a point. Did that point make sense then? Okay. No, I will make sure I'm clear.
Well, they're the same.
Because they look the same otherwise. Any other questions on that? Okay. The point I want to make here then is that you can do all of the translations on this graph that you could have done on other graphs. For example, what if you put a number in front of the square root sign? What would that do to the graph?
Flip it.
Well, let's say it was like a 2.
Oh.
Say there was a 2 there. It would
Stretch it.
this
Stretch
way.
it vertically.
Vertically over the x-axis.
Over the x-axis, yes.
Isn't it? Yeah.
Stupid question.
What if there was like a negative inside the brackets? What would that do?
Flip it onto the other side of it.
Yeah.
Over, it would flip it over the
So what
vertical.
would that be? Would that be like
So should I do an example here? Let's graph y equals 2 negative x plus 4. Can you guys throw this in your graphing calculator? Y equals 2, then absolute value negative x, then add 4.
Square root.
Square, yes, square root all that. So, did I say absolute value again? I always do that. I like save wrong functions. 2
And try and make us figure it out.
square root. Oh, I know. I'm the worst teacher. Okay. So what happened to this graph? It's been stretched up a little bit.
Flip.
It's also been flipped like side to side,
4 up.
and then it's been moved 4 up. Does that make sense?
So 2.
So this minus sign flipped it side to side. This 2 has made it kind of taller than it normally would go. And this plus 4 means that it now starts up here at...
4 minus.
What was that? But we can't have a bottom part because it's not a function. Right? Like you're talking the bottom half of the parabola. It will never show up unless you force it to because it's not a function.
So the main difference is like
So like if you wanted to make it show up, you'd have to do this. Negative big bracket 2 root x, 2 root negative x, close bracket, plus 4, close bracket. You see how I'm throwing like a negative sign in front of everything, and then that would then make the other. No, that won't work because now I flipped it over that axis there.
Is there not?
How am I going to fix this? There's a way of doing it. Let me try.
Did you have to put minus?
Let's try this. This might do it.
Are you just trying to? Like,
There we go. That would get it there.
How'd you do
So
it?
all I did here, Birdie, is I put a negative in front of just the 2, but not the 4 on the outside, and that got the other half. That being said, we rarely, if ever, even want this other half, though, because then it's not a function and we don't work with. Does that make sense? Okay, let me move on here. I think you guys got this concept. Could you guys graph this function, then, without using a calculator?
Maybe. Okay, well, you can start with the original and then apply.
Okay, so let's start with the original. The original square root graph looks roughly like this.
So the -5 outside would move it -5.
Okay, so Aiden suggests start with the -5 outside. The negative is going to make this guy go upside down. The 5 is going to make it 5 times taller, right? So the -5 right here is going to make this graph go like...
Wait, that would make it taller?
Because the 5 is outside.
And then the -1 would move it to the right.
Okay, so then the -1 would take this guy, and I can do this, but you guys can't. I can pick this thing up, and I can move it 1 unit this way,
2 units down.
and then 2 units down.
Why do you
But I thought you couldn't have negative.
What was that?
Why are we doing
Well, the blue one is what the graph should look like when I'm done,
Oh, stretch it by 5.
right? So I flipped it upside down, I stretched it by 5, I moved it over and down. You guys okay? Okay. You know how they're on quadratics, there's vertexes? This thing doesn't really have a vertex, but this point right here that was at 0, 0, it is now at 1, -2.
So that's where it starts.
That's where the graph literally starts. Like the first y value you can possibly have is -2, and the first x value you can possibly have is 1.
And then it's the element.
So like if I were to ask you for the domain, you would say x has to be greater than or equal to 1. And for range, you would say y has to be less than or equal to -2.
So is the red graph just a regular X?
Yeah, the red graph was my attempt at like a regular x squared graph, and then the blue graph is what it's going to change to. Now, if you guys need to, you can use your calculators. It's just I want to practice those skills so that you're fluent in them, so you're not always going to your calculator.
I'm gonna need more practice.
Okay, let me move ahead to some final stuff here. I'm going to skip this slide too. I'm going to go to this guy here. I'll come back to those slides when I get time tomorrow. Just remind me. One of the other things that we've learned how to do in the past with square roots is solve equations involving them. This is actually what the -1 grade 11 class is doing right now. Do you guys remember this at all?
Yeah.
What, like you have to...
How to solve this? Do you guys remember how to solve an equation?
Yeah, you
Correct.
want... Yeah.
Square.
How do you solve something that has a square root?
Square.
Okay, but before you square it, you want it to be by itself.
Right.
You gotta-
So you have to get rid of your -3.
So like on this guy right here, this we need to divide by -3. Divide by -3 to get rid of it. So now your square root sign is by itself, but it's equal to -3.
Yep.
Now I can square both sides, so then 3x over 4 would equal 9 again. Times up the 4, so 3x would equal 36, and divide by 3.
Sweet.
We did this last year. I made you guys practice it a lot because I knew you were going to need it this year. So how about this? We got 10 minutes left. Why don't you guys try solving the remaining 3 of these guys here?